Ladies and gentlemen, a pleasant morning to one and all. I am Dr. L. Ruby Nirmala, Assistant Professor of Physics, M.V.Muthiah Govt Arts College for Women, Dindigul. I hope you guys are doing well. Let us consider this ample of time as a gift of our Lord Almighty to enlighten, enrich, and enhance our knowledge. A famous quote by Albert Einstein: science can flourish only in an atmosphere of free speech. Yes, the postgraduate Department of Physics, M.V.Muthiah Govt Arts College for Women, Dindigul, has the pleasure in inviting you all for the international webinar on multifunctional nanostructured materials. Light symbolizes brightness and prosperity. With this noble thought, let us start this morning by lighting the lamp. I would like to call upon Dr. R. Rajamal, Head, the Department of Physics, to welcome the exuberant participants. Over to you, ma'am.
Good morning to all of you. It gives me immense warmth and great pleasure to grace all of your presence in the interest of entire committee. It gives me tremendous contentment to be presenting the welcome speech among us the most esteemed personalities who have accorded us in their respective fields. I am very glad to welcome you all for this international webinar on multifunctional nanostructured materials organized by our PG Department of Physics, M.V.Muthiah Govt Arts College for Women, Dindigul. I welcome Dr. Lada Puranam, Principal of our college, who has rendered her encouragement and constant support to conduct this webinar. And I welcome the speaker, Dr. M. Kumaresavanji, Assistant Professor, Department of Physics, National College, Tiruchirappalli, and speaker, Dr. Anthony Anand, Research Professor, Department of Chemistry, Sunganbon University, Republic of Korea. I thank them for accepting our invitation within a short notice. And finally, I welcome all participants of various colleges in and around Tamilnadu and others for this international webinar. I ensure this webinar will be very profitable and fruitful for everyone present here. Thank you.
Thank you, ma'am, for your warm welcoming. I'm really privileged to have the pleasant task of introducing our guest speakers now. Define success on your own terms. Achieve it by your own rules. Yes, as the course, we have two eminent speakers in our midst. Dr. M. Kumaresavanji, Assistant Professor and Principal Investigator of Nanomaterials Laboratory in the Department of Physics, National College, Tiruchirappalli. He has received his doctoral degree in physics in the year 2010 at Brazilian Center for Research in Physics, Brazil, and he obtained his master's degree in Bharathidasan University, Tiruchirappalli, Tamilnadu. He was the postdoctoral researcher from the year 2012 to 2017 from the Department of Physics and Astronomy, Faculty of Sciences, University of Porto, Portugal. He has been the proud recipient of many awards and fellowships, and his ongoing research project is enhancing magnetotransport property in nanostructured materials worth of rupees 18 lakh and 15,000. He had published 23 research papers in an international scientific journals with high impact factor. He presented 12 papers in international scientific conferences and seminars. And also, he had delivered several invited talks based on nanoscience and nanotechnology. He's serving as a reviewer in 6 journals, and he has a number of collaborative works with different research groups in Brazil, Portugal, Russia, Tunisia, and Morocco. Currently, he is working in the field of fabrication of nanostructured materials, nanoporous alumina templates assisted nanosynthesis, magnetic properties of nanomaterials, materials under extreme conditions. In this verse, I assure that we all will be benefited greatly by paying thoughtful attention towards him on the topic magnetic nanostructured materials by template assisted method. Over to you, sir.
Thank you, ma'am. Thank you for your introduction. And I'm pleased to be here as part of this webinar. I'm also thankful to the principal, the head of the Department of Physics of M.V.M. College, and Dr. Ruby Nirmala for organizing such a nice event and inviting me for this webinar. For the first session, I'm going to talk. Let me present my screen. Yeah. So can you see my slides, please?
Yes, sir.
Okay. So in the first session, I'm going to talk about nanostructured materials by template assisted method. So we know all about that nanomaterials. So we are now talking about nano everywhere. Yes. So we have nanomaterials, but any materials at the nanometric scale, if they have any different structure, that is called nanostructured materials. Such kind of nanostructured materials can be easily fabricated by template assisted method. If you see the nanomaterials, the prefix nano is a Greek word that means dwarf. Sorry. So can you see my presentation? Can you see my presentation? Yeah. Is it visible?
Yes, sir. Visible, sir.
Oh, yes. Okay.
Yes, sir. Yes, sir. Thank you.
So if anyone wants to see my presentation, please tag Kumare Savanji's presentation, please. Okay. So nanomaterials, the prefix nano means the word is from Greek word, and that means dwarf. So by definition, any materials that have at least one dimension in nanometric scale, that is 1 to 100 nanometer, is called nanomaterials. It is the size that 1 billionth part of 1 meter, that is 10 power 9 meter, 10 power minus 9 meter. For example, our blood cell is about 500 nanometer, whereas the hydrogen atom is 0.1 nanometer. Just to show you the different dimensions of different materials, I suggest you go to this scale of universe, that website. Here I have opened that website in my, you can see here. So the scale of universe.com. If you go there, you will see a flash player like this. So here you can play or you can see different materials with the different dimensions. For example, here I have human. So if you want to see the description of this object, you can just click on that. So human is about, is the average human, is about 1.7 meter. So now I'm going to just maximize this thing, okay? So in the bottom, you have this bar to maximize or minimize. So if you maximize, you can see giraffe, elephant, that are the bigger than us, yes. So that scale will go up to our observable universe. That is like our galaxy, our neighboring galaxy, or the whole universe, yes. the observable universe. For example, Eiffel Tower. If you click the Eiffel Tower, you will see that it is about 320 meters inland. So like this, it will go. It will go. It will go up to what we can observe to the materials different dimensions. Okay, let's back to our point, that is nanomaterials. So I'm going to minimize this one by using the bottom tab. Okay. So here we are, that is human, and this is 1 meter scale. Okay, within this 1 meter scale, what we have like a humming bird, that is about let's say 10 centimeters. And if you go again further, so ant maybe it's like 4 millimeters. And if you go like you can go the millimeter scale. This is the millimeter scale. And again, if you go further inside, you will see the micrometer scale. So this is the human hair. Human hair is about 100 to 60 microns. So our normal eyes, that is our very healthy human eye, can see less than about 50 or 30 microns. If you see the lowest object, we need we need microscope. Okay, optical microscope. If you go further, this is the micrometer scale and the violet light wavelength. And further, if you go, we can reach the nanometer scale. Okay, this is the nanometer scale. So if you see the nanometer scale, so the atoms and molecules are around here. So now you can understand how the materials, different materials are with different dimensions. This is very interesting, not only for us, but for also for children. If you have children in your home, you can show them how it is different materials. Okay, so if you go less than 30 micron, we need a microscope, and if you go nanometer size, we need electron microscope. So due to this fascinating properties of nanomaterials, such nano becomes a separate field like nanoscience and nanotechnology. So that includes physics, chemistry, biology, or engineering, everything. Okay. So here I just show how we divide the materials by the dimension. So nanoparticles is called 0 dimensions, because if a material, if you say a dimension, it should be more than a nanometer. In the nanoparticles, there is no dimensions at macro scale because all 3 dimensions are at nanometer size. Whereas these nanowires and nanotubes are called one-dimensional because only one dimension, that is along the axis of the tubes or wires, is the macro scale, whereas the perpendicular to the tube, it is nanometer scale. Whereas the thin film is called 2-dimensional materials because the 2 dimensions are at macro scale, whereas the bulk material is called in 3 dimensions because all the 3 dimensions are at micro scale. So here I show how we can separate that different kind of nanomaterials, let's say. Because organic nanomaterials are inorganic nanomaterials. Whereas the polymeric micelles, dendrimers, polymeric nanoparticles, and liposomes comes under organic nanoparticles. Whereas silicon nanoparticles, gold, or carbon materials, or magnetic nanoparticles are inorganic nanoparticles. These organic nanomaterials max 1 centimeter. Okay, so I am going to measure the total surface area of this cube. So it is 6 centimeters square. Now the same cube I am going to cut into all 1 millimeter cubes. Then I measure the surface area of all the cubes, that will come 60 centimeters square. Now the same cube I am going to cut in all 1 nanometer cubes, and now I measure the total surface area, which comes about 60 million centimeters square. So see how I can increase the total surface area of a bulk material from 6 centimeters square to 60 million centimeters square. Why we are talking about this total surface area? Because if you get total surface area, that is a higher surface area, we get more atoms on the surface, and it can interact with other particles very easily, and that is act as a catalyst that we need in every applications. So not only higher surface area, also these nanomaterials are small enough to fabricate comfortable devices, and also the size of the nanoparticles are comparable to our living beings. So if we can achieve that nanomaterial in devices at this stage, we can use it very comfortably. As I said earlier, that nanomaterials are important for their large fraction of surface atoms, large surface, so that they gain large surface energy. So it gives the spatial confinement, and also due to this confinement, we get the reduced imperfection. Due to these behaviors, these nanomaterials gives good fascinating properties, different thermal properties, mechanical properties, optical, electrical, and magnetic properties, which is different from the bulk one. For example, thermal properties, we can talk about melting point, and mechanical properties, we can go for strength, elasticity, and tensile strength. And for optical properties, we can go for absorption and scattering of light. Whereas the electrical properties, when you come to nanometric size, we can talk about the tunneling current, because of the nanometers is about some dimension of molecule. And magnetic properties, so we can achieve superparamagnetic behavior once we reduce the materials to nanometric size. For example, here I show the optical behavior of gold nanoparticles. We know gold is a yellowish color in bulk form. Just see here, when we reduce the gold gold to nanoparticle dimension, the color, this is the suspended nanoparticles, that is color change very drastically. So if the gold nanoparticle is about 80 nanometer, then it shows a pink color, and 50 nanometer shows a red one, and 20 nanometers it shows a light orange one. So from this it is very clear that the nanomaterials give different behavior than their bulk one. And another one best example is allotropes of carbon. We know carbon is materials of future. Everybody is talking carbon. Yes. Carbon is the future material because of its very fascinating and very alternate. It's a very good material. Only carbon is 6 electrons. So we have in bulk form we have a diamond and graphite. Diamond is very hardest material and very high melting point. Of course, graphite is very soft material and it is not elastic and good electric conductor. So if you reduce the graphite to a nanometer size, the 2-dimensional nanometer sheet like graphene, because graphite is made up of different sheets of graphene. Yeah? So if you remove one sheet, that is called graphene. But the graphene shows one of the strongest material in the universe, whereas the bulk of graphite is very soft material. Just see how its mechanical properties change drastically. So it is the graphene is the strongest material. It has excellent tensile strength, and it's a transparent material and good electrical conductor. So now I'm going to roll this graphene to form the nanotubes. Yes. If you form the nanotube, it also shows very good conductor. It gives the electrical conductor along the axis of the nanotubes, whereas the perpendicular to the axis, it is not that much good conductor. Also, it is 20 times stronger than steel. That is, I'm talking about the carbon nanotube. Okay. And also, it is highly elastic and bend without breaking. And it's also stable for a very high temperature. And let's see about the fluorine. It's also one of the allotrope of carbon. Due to this fluorine formation C60, that is 60 carbon atoms, it has an electron deficiency. That means it possesses high electron affinity, and also it exhibits hydration and dehydration, which is suitable for hydrogen storage material. See, this material from bulk to nano, it changes very drastically this behavior, mechanical and electrical magnetic properties, not only by nanomaterials, but when I change the nanostructures, it changes their property also, right? So now we are going to talk about the nanostructures. Not only nanomaterials shows good excellent property, but depends on its structure. It shows different and very fascinating property because of its shape anisotropy, what we call shape anisotropy, or the property of this, let's say the nanotubes, it's anisotropic property. Along the axis, it shows one property, and perpendicular to the axis, it shows another property. Uh, for example, the nanotubes, we have more higher surface area than the graphene because it has the hollow structure. Yes. So not only nanomaterials, but also the nanostructures. When we become the different structures, it's exhibit different properties, different and of course very interesting properties. That is very good for our potential applications. So here I just show some of the nanostructures. Nanostructures means any material that have different structures at nanometric scale, right? So these are the core cell nanostructures. These are the nanoparticles-based hybrid nanostructures or heterostructures. We can prepare many kind of nanostructures by template system that I am going to talk about actually. So what are the applications now we have already? So there are many applications we have about the nanotechnology. For example, that create a silver bandage which uses silver nanoparticles. As I told that nanoparticles that can enhance the activity with the wound maybe in the case of the bandage. So it is at nanometric scale. It can easily it cures the wound very quickly, and also that pants from the Eddie Boyer that is wrinkle free, and the tennis balls coated with nanoparticles. It is more stronger than the normal particles. And the Samsung also using the nano silver silk refrigerator to get better insulation so that we can save the energy, of course. And some high-end brand cars also using nanoparticles to reduce carbon emission. They're using some kind of nanoparticles to reduce carbon emission. And also, they use scratch-resistant glasses. That is, the glasses are coated with some kind of nanomaterials that is very resistant to the scratch and also fog resistance. So fogs won't form on the glasses because that is that hydrophobic behavior can be get once you go for a small angles, that is nano angles cut in the glasses. Also, they are using scratch resistant paints on these cars. Another one important application for nanomaterial is nanomedicine. So here I show a comparison graph just to see. Okay, so plant cell is about 100 micron, whereas animal cell is about 10 micron, and virus is about 10 to 100 nanometers. So now we are all, of course, affected by the virus. Anyway, so if we can reach this region, we can easily find this virus and we can cure, right? And also we can deal with the animal cells. So nanomedicine is used to monitor, repair, construct, and control the biological systems at molecular level using nano devices. Most animal cells, as we know, are 10 to 20,000 nanometers in diameter. Nano devices smaller than 100 nanometers would be able to enter the cells and organelles where they could interact with DNA and proteins. So these nanomedicines are very interesting and of course very affordable for the medication. For example, here I show another one picture that is every material is made up of atom, then molecules become macromolecules, that become the organelle, then cells, tissue, then our organ system, then all the organ systems formed our organism. So if we can reach this level, that is the macromolecule level, that is the nanometer size, we can easily cure any disease or easily we can identify what is happening in our body. Right? So in the nano devices in the medical field are used for drug delivery systems, apoptosis detector, gene therapy. If you have any problem in the, for example, in the future, like they can just extract the gene and they can just change the coding. That is called the gene therapy. And then they will let you, they will inject this, repair the gene into your body, then it will be cured. So in the future, you won't have that kind of disease. Okay. Also, the nanosensors, disease locators. For example, nanosensors to find where the plaques are or the blood plaques are formed, and disease locator also where the cancer cells are available. So you can just send some nano devices that is prepared by nanomaterials, it will easily identify such kind of cells. Okay. So another very important application is nanosensor. Nanosensor is just like a microchips. Okay, it is made up of nanomaterials. You can just insert under your skin that will monitor your blood pressure, your glucose level, and your heartbeat, your temperature, and it is easily send messages to your mobile automatically. So if you want to monitor any patients, these kind of sensors are very interesting. So I'm going to show some chips into the body, or let's say microchips in hands allow you to pay for goods in UAE. That means nowadays in the Western last 3 to 4 years, they're eager to insert such kind of microchips prepared by nano materials, of course, nano devices under their screen. These microchips acts like everything. For example, in our country, let's say it is connected with your ration card, your Aadhaar card, your passport, your PAN card, your driving license, your bank account details, everything. So if you insert that chips under your skin in your hand, you can pay everywhere. Like you don't need to take any money, any credit cards, any debit cards. You just go just with your hand. You just buy the things and you tap where the sensor is implanted to the sensor to the detector, and it automatically detects the money from your account. Also, if you are traveling abroad, you don't need any passport in your hand. Everything is inserted or everything is connected with your microchips. And also the bank accounts and also your driving license, everything will be linked to your microchips. And this will come for sure in our country. I hope in maybe in 1 year. As our central government is implementing that digitalization everywhere, I hope this kind of microchips will arrive our country quickly. And also India is a very big opportunity for corporate companies. Of course, we have manpower, huge manpower. For sure, they will implement such kind of microchips. So you will see it is in recent days. Okay. So another very good application of nanomaterial is the nano energy. So you see, we have a solar cells to it's a green energy, though, so we can get energy from the solar. But if I use nanomaterials instead of bulk material, I can get more surface area that photons can absorb. It can absorb the photons in more surface area. So the capacity, that is the efficiency, will be increased a lot. And also the storage capacitor, that is supercapacitors. So we have a solar energy that produces production and energy storage. Also nowadays they are using different nanostructured materials that will charge very fast and recharge very slow. That is the supercapacitor. So for such kind of actions, nanomaterials, not only nanomaterials, but nanostructured materials. So as this nanostructure changes, also its efficiency also changes. So now they are looking for a very good efficiency using such kind of nanostructured materials. Another one is the nano energy generators. These are old one actually. Yes, thermoelectric generator, piezoelectric generator, or triboelectric. So these are work like thermoelectric are work with the two ends with the different temperatures, and piezoelectric just by processing it produces electricity, whereas triboelectric produces electricity when it has a friction. These are worked by my colleagues in the University of Porto. They were producing very minute level, micro level nano devices, so that you can fix such kind of nano devices under your smartwatch or even in your under your dress or your shoes, so that it can produce small amount of electricity that can recharge your small electronic gadgets. For example, your smartwatch, you have to recharge every day, right? So if you insert such kind of nano energy generator under your smartwatch, it will automatically recharge your gadgets. So come to the point that it is nano fabrication. Okay. So how we can fabricate such kind of different kind of nanostructures? We go, as I said, there is many kind of nanostructures, and we have two approaches to fabricate such kind of nanostructures. One is top down, and another one is bottom up. So in the top down, you just take a bulk material and reduce to its nanometric size. That will come to your nanoparticle. It is achieved by milling mainly, milling or grinding, something like that. And also for bottom up, you just take first the ions or the atoms, then it will form clusters, then the nanoparticles will come. For example, solvent synthesis, you just dissolve your materials in the liquid, then the atoms will form in the liquid. So once you heat or you add some gelation agent, then these atoms will form a clusters. Then if you increase the temperature, then clusters will become the nanoparticles. Right. So there are two approaches, top down and bottom up. Whereas using these approaches, we have many kind of nanofabrication methods. Here I just emphasize some fabrication methods like template-assisted method, hydrothermal method, sol gel method, co-precipitated method, lithography, sputtering, pulse laser deposition, wafer deposition, and nano imprinting. So in this, I'm just interested on this template-assisted method because it is cost-effective, and also, as I told, we can we can fabricate a wide variety of nanostructure materials. So while we're talking about template-assisted method, we have a template just like a substrate with nanopores. Okay, so these nanopores can be different shapes, can be created while we fabricate such kind of templates, and also such nanopores work as a model. So we have different kind of nanoporous templates. They are alumina templates, polycarbonate templates, and organic templates. Whereas these polycarbonate templates and organic templates are cannot withstand at high temperature, and also they dissolve at many. It is not stable at many chemicals. So alumina template can withstand up to 850 degrees Celsius. After that, it crystallizes. But also the alumina template, that aluminum oxide I'm talking about, the alumina template is stable for most of the chemicals. So while we preparing this alumina template, we can tune the nanoporous size. We can get nanoporous size depends upon our requirements, and also we can change the interpore size. We can change the nanopore length, and also it is stable in most of the conditions. So I'm going to talk about this nanoporous alumina templates. So just by using these nanoporous alumina templates, we can prepare many materials like nanotubes, nanowires, nanorods, nanopillars, multi-segment nanotubes, nanowires, nanopolaris, nanoannealers. These are the materials prepared by my colleagues from University of Porto. That is the nanopolaris, nanopillars, multi-segment nanowires, so nanorods, something. So I will show how we can prepare the alumina templates. So alumina template preparation is very easy step only. We need to do anodization. For this, first we take high pure aluminum foils that we cut into 1 into 1 centimeter square. Then we do the leveling, because while it coming, it comes by roll, right? So we just cut it, and first, then the aluminum is easily oxidized with atmosphere. So we need to first do the electropolishing. Before the electropolishing, we clean the alumina template by acetone and ethanol, and then we do the electropolishing using perchloric acid at 20 volts for 2 minutes. Just I show here the setup, that electropolishing setup here. So after you do the electropolishing, you will get a mirror surface like aluminum foil. So then the aluminum foil is fixed in a Teflon cell, which one is made in our lab, actually homemade setup. So in the Teflon cell, we just fix the aluminum foil. Then we fix in the bottom the copper plate. Okay. So here you can see small portion of the hole. This is the aluminum foil, which is attached with the copper plate. Then we attach the both. then your copper plate is like as a anode, right? So then we place the platinum mace and we pour the electrolytes. So depends on the different electrolytes. If you do the anodization, you can get different pore size. For example, phosphoric acid you will get a 20 nanometers, and oxalic acid you will get a nanopore diameter of 35 nanometer, and phosphoric acid you will get about 180 to 200 nanometers. And also with the different electrolytes, we have to deal with different potential and different temperature. So this is I show how it is going. Like, so first when you start the anodization, the first process, the aluminum oxide will form. That is we call the barrier layer. So once the barrier layer form, in the second step there will be a steady state pore structure is formed by closely packed cylindrical cells. Then the oxide grows at the interface oxide or aluminum as a result of the outward migration of oxygen ion. Once we increase the time of anodization, the pore length will increase. So we can easily tune the pore nanopores diameter and pore length just by controlling the anodization condition. So here I just show how the alumina template, the nanoporous template is available. Like so, we have aluminum foil. So alumina barrier layer. This is pore and pore diameter and inner pore distance, and this is the anodization alumina layer. So after that, we can just clean. We have to clean because we have anodized it with different acids, right? So we have to clean it. So here I show some same micrographs of three different nanoporous alumina templates. This template is prepared by phosphoric acid, which the nanopore about is 180 nanometer. Here it is prepared by sulfuric acid. The nanopore is about 15 nanometer. This is prepared by oxalic acid. It's about 40 nanometer. So you no need to think that it is only 15 and 40 or 180. So we can enlarge this this pore size also. If I want to get 60 nanometer, I can do the pore widening by some chemicals. So chemical etching method, I can widen the pores. So I can get like 60 or 70 or 50 nanometer, or like 20 or 30 nanometers, or in this case I can get 200 or 210. So also the barrier layer also can be removed by chemical etching. So to prepare the nanotubes, nanowires and nanorods, we go for electrodeposition sol gel method. Whereas nanopolarize and nano-only-dots, we go for thin film coating by pulse laser deposition and sputtering or spin coating also you can do for such kind of preparation. So here I show how our colleagues are doing the nanotubes or nanowires by electrodeposition. So this is our prepared nanoporous template, right? So here is the aluminum foil, so alumina layer and nanopores. So first we remove for the deposition, electrodeposition. First we remove the aluminum by chemical etching. Then we remove the alumina layer also by chemical etching. So now we have a pore in the nano templates. Now we coat this bottom of this template by gold by using sputting technique. So that will act as a electrode, right? So now we fill the electrolytes what we require and we do the electrodeposition. So by doing this one, we can get nanotubes. Here I show some micrograph of nanotubes going from bottom to up. Okay. So by changing this electrodeposition condition like timing or electrolytes molarity or pH value, so we can control whether it is nanotubes or nano wires, and the thickness of the nanotubes walls also we can change. So this is the setup used in our lab to prepare the nanotubes. Here I show that nickel nanotube preparation and same micrographs of the same. So another one interesting thing is the multi-segmented nanowires. Here I show that nickel copper multi-segmented nanowires, like nickel copper nickel copper nickel copper. So such kind of multi-segment nanowires can be achieved by pulse electrodeposition. The same method, we just pour two kind of electrolytes, okay, nickel and copper electrolytes. Then each one reacts with different potential. For example, here 0.1 volts, it reacts one material, and whereas the 1 volt, it reacts another material. So if we apply like pulse electrodeposition, we can prepare such kind of multi-segmented nanowires or nanotubes also. So it is achieved just by optimizing the time, the applied potential, and the electrolyte. And these kind of multi-segmented nanowires are used for delivery of multiple drugs. And another one important thing is the core cell nanowires. Here I show that core cell, the deposit of core cell nanowires. First, you prepare the nanotubes, then with one electrolyte, then clean it. Then again, you put another electrolyte that we have to deposit inside the nanotubes. So now the by electrodeposition, the other material will deposit inside the nanotube. This is called the core cell nanowires. So this you have to do with two different electrolytes with 2 times. So this kind of core cell nanowires or nanostructures enhances the photovoltaic cell, also acts as a semiconductor junction and used as a high-speed transistor. So preparation of nanotubes by solder. These are the electrodeposition method what I was talking about. But with simple method like solder. So for electrodeposition, we need a constant current source or electrodes, very good electrodes. Whereas for solder method is very simple and very cost effective. So for first thing you have to prepare the solder for your material what you want. That you have to prepare solder. It should be more viscous material. Okay. Then you have to insert that immerse that nanoporous template inside the sol gel. Due to the capillary action, the sol gel will enter inside the nanopores. So you just leave it 2 or 3 hours, depends on what you want. For example, if you leave it for a few hours, it will form a nanotube. If you leave it for many hours, it will form a nanowires or something like that. So you just remove the nanotubes, then you heat it, then the salts that is absorbed on the walls will form a nanotube formation. So this is another one very easy step to prepare such kind of nanostructured materials. Here I show how I prepare that lanthanum strontium manganese oxide nanotubes by template assisted sol gel method. For that, I first prepare lanthanum strontium manganese oxide sol gel. Then I immerse the alumina template inside the sol gel. Then I remove the templates and calcinated at 800 degrees Celsius. Okay. Here I show some SEM images. That is the top view of SEM micrograph and the cross-sectional micrograph of that nanotube. So it is most of the nanopores are filled with this sol gel that is formed the nanotube very clearly. It can be seen very clearly. And another one thing I have prepared is nanofolares. Nanofolares I can prepare from the same sol gel. I told about the sol gel, right? You just try the sol gel, you will get a aerogel. Then you calcinate it, you will get a nanopowders. Then you press it to make a pellet. Okay, from sol gel we can make a pellet. So the pellet is used as a target in the pulse laser deposition, and you target the pulse laser on your target. A plum is created which will deposit on your nanoporous alumina template. So nanopolaris is nothing but a continuous thin film, but with nanopores, ordered nanopores among these. Okay. Here I just show some of the SIM micrographs that I have prepared for lanthanum strontium manganese like the nanopolaris. For the same, I have prepared the LSMO sol gel. Then I prepared a pellet from LSMO. Then the pellet was used as a target in the PLD, pulse laser deposition. So just by increasing the deposition time, for example, here I deposit for 10 minutes, here I deposit for 20 minutes, and here I deposit for 30 minutes. So you can see the materials are deposited deposited in between the holes. Okay, so these are the continuous films, yes, and with nanoholes in between. That is we call the nanohole arrays. As I told you earlier, we have different nanostructures. We have different properties, not only magnetic but electrical properties. Okay, so from this one, from the start, what I'm going to tell that from solder and preparation of alumina template, we can prepare different kind of nanostructure materials. For example, from so if you have a solder and alumina template, from solder you can get nanoparticles, and with both solder and alumina template, you can get nanotubes and or nanohole arrays. So in summary, I would say that nanoporous alumina templates can be prepared by simple anodization process. These templates are easy to prepare and the aspect ratio can be tuned in easy manner. And alumina templates are compatible to fabricate various nanostructure materials. I would like to also emphasize that I prepare my materials for the study of magnetic refrigeration. So I prepare the different nanostructure materials and I check their magnetic entropy change, which is important for the magnetic refrigeration application. So I would like to acknowledge my project, the DST Sir project, and Professor K.K. Nanda from IIT Bangalore, and my former colleagues, Dr. João Pedro Araujo and Armandina and Celia Sousa. Okay, thank you. So if you have any questions, please feel free to ask.
Thank you, sir, for the informative presentation.
Yeah, thank you, ma'am. So,
On
is there
behalf
any
of the
questions?
participants,
They have posted in chat box. Okay.
Yes, sir.
Yes,
It's in the chat
please
box,
go
sir.
ahead.
On behalf of the participants, I'm representing some questions to you, sir. Carry on.
Yeah.
In what pattern the CNT has been formed, and what kind of layer CNT can be arranging? One of the participants, Divesh.
CNT depends on, we have different kinds like chiral or armchair. Depends on our preparation method. It can be changed. The different kinds may be changed. Yes.
Another question: what is the specific nano devices used for disease locator?
Okay.
Specific nano devices used.
Yes. Mainly some magnetic kind of, because we need we just send the nano device inside the body, then we have to find that things. Okay. So just by applying small magnetic field, we can find such kind of devices that they are using. What I say that magnetic nanomaterials, magnetic nano devices.
Okay,
Yes.
Can you use fullerenes in a photovoltaic cells to enhance efficiency, sir?
Yes. Sorry, C60 for?
Sir, can we use fullerenes in photovoltaic cells to enhance efficiency?
Sorry, I couldn't get your point. C60 for photovoltaic cells.
Yes, sir.
Photovoltaic. Yes. There are works are going on. Of course, you can not only C60, but you can make it more like C70 or something, C72 or 166. You can get more carbons in the buckyballs, and you can they are testing their efficiency, of course. Yes.
Then another question is, how can we use nanotechnology in archaeology?
Archaeology, yeah. Okay, sorry, I don't have idea about archaeology, but of course, to find the carbon dating, sorry, I don't have idea on archaeology, sorry.
And why graphene has a zero band gap, sir?
Why graphene?
Yes, sir.
Yeah, once you reduce the nanostructure, as I said, its optical property changes, right? So because, for example, in graphite, that each layer has a gap of like 0.35 nanometers, right? And also the graphene sheets, that very small sheets that contains only small atoms, like only few atoms. So once you reduce the material to nanometric scale, this optical property, as I said, optical properties, mechanical properties, everything is changed, for sure.
What are the advantages of having high surface ions?
High surface ions. As I said, it is that higher surface always induce catalyst. used as a catalyst that can enhance the activity with the atmosphere. Okay, atmosphere means which material it is reacting nearby, so it can enhance the activity, the reactivity. So the ions, of course, it will bind better, or it will donate or receive the electrons better than the bulk materials. Yes.
Yes, sir. Then the last question is, nano templates are used in solar cells applications. Can you use it?
Yes. Uh, for example, I forgot to mention, of course, that if you prepare nanomaterials without template, it is randomly oriented. For example, if you prepare a nanotube, okay, just by other method, you will get a nanotubes randomly oriented, right? But in the template assisted method, if you prepare nanotubes or any other nanomaterials, it is mostly ordered. Okay, you understand the order. That is, each tube is parallel to each other. So these highly ordered nanostructured materials again gives you better efficiency than other nanostructured materials. So they are, of course, it is good to go for highly ordered nanostructured materials in this case. Yes.
Yes, sir. The last question, sir.
Yeah.
How to prepare sol gel gold nanoparticles, sir?
Sol gel. There are some reagents. So it is very easy. You can find in literature, of course. It's very easy. You can just solve that reagents inside the solution, that is ultra pure water. Then you have to reduce the water content, and you can add gelifying agent, something like ethylene glycol or something like that. So you will get a sol gel, very like a viscous solution. That is we call sol gel. Yes. Other question?
Yes, sir. So due to the time consumption of some questions, we can skip it. I kindly request all the participants to wait for the reply.
Okay.
Thanks, sir. Thank you, sir. Thank you for the
Okay,
informative presentation, sir.
Thank you.
Now, we will move on to the next session. It gives me an immense pleasure in introducing our resource person, Dr. Anthony Onand. Dr. Anthony Onand is a Brian Korea 21 plus research professor in Sankyoung University since 2016. Currently, he works in the application of vacuum and atmospheric pressure-based plasma techniques such as PECVD of thin films for sensors, nanomaterials preparations for biomedical fields, and plasma seeds treatment. He has contributed a lot to the field of shape-selective nanomaterials preparations using plasma assistance, which granted a Korean patent in the year 2014, and it was transferred to a company also. He has successfully completed a research project funded by National Research Foundation of Korea worth rupees $90,000 recently. He received his PhD in the Faculty of Applied Energy Systems from Jeju National University, Korea in the year 2015. His research was mainly focused on the dielectric barrier discharge plasma assisted metal oxide nanomaterial preparation for catalytic and biological applications. He obtained his master's degree from Anna University, which is M.Tech Nanoscience and Technology, and MSc Physics in Madras University in India. He is a recipient of Young Scientist Award from Indian Membrane Society in the year 2017 and published 2 book chapters. He is serving as a reviewer in 8 journals and acting as a topic board member of quoting journals. He closely works with different research groups in Korea and globally. Now he is going to deliver this consequential lecture on the topic, the cyclohexane based gas sensors using PECVD and plasma assisted nanomaterial preparations. Over to you, sir.
Hello? Hello? Hello?
Yes,
Can
sir.
you see that?
Yes, sir. Yes, sir. Okay, continue, sir.
Okay. Good afternoon, respected Madam Head of the Department, Madam Rajamal, and Organizing Secretaries, Madam Dr. Nirmala, Ruby Nirmala, and dear participants and respected staff members from various colleges. I thank you so much for this opportunity to interact with you and to present my research, which is carried out in Sangin University and during my PhD. And right now, I am in my research professor activities. Okay. I, I want to, in this presentation, I would like to discuss two things. Just a moment, I would like to stop my camera. Okay. Okay, can you see me right now? Hello? Hello? Madam,
Yes,
can you
sir.
see the presentation? Can you see the presentation?
Yes, sir.
Okay.
Wait to see, sir.
Okay, in this presentation, I would like to discuss two fields. Those are, first one is the gas sensors, and then the second one is the plasma-assisted nanomaterials preparation. As Dr. Vanji has talked in detail about the nanotechnology and basics of nanoscience, starting from the size and shape, and then the surface area and those things. Nanotechnology is gaining momentum for the past 2 decades, and the size and shape that helps in various applications, because many applications depends on the size and shape of nanomaterials. In this one, the first topic I would like to discuss about the gas sensors based on cyclohexane. Usually, the gas sensors are based on metal oxides. It is usually the metal oxides are high temperature sensors. So that is why in this research I have taken the organic polymer based gas sensor. So the usually the polymer material polymer the organic materials uh, are having good dielectric and optical coating, and then to inhibit corrosion. These are the materials are used for these kind of things. But usually the organic materials are mainly utilized to prepare low dielectric constant materials in chips, but it is not mainly used for a gas sensor because it is operation temperature is very low. So we have to make it as a polymer. So if we make it as a polymer coating using various deposition technique, we can utilize as a gas sensor. Usually in sensors, the 3S we have to consider. One is the stability, sensitivity, and selectivity. So these three things are fundamentals in gas sensing. So for metal oxide sensors, its sensitivity and stability is very low because it is usually operating in high temperature. So these 2 points, sensitivity and stability it lacks. So when we use the organic materials, we can try to enhance the selectivity, sensitivity, but at the same time, it's a stability. It's also a problem. So there is a kind of how to say we have to adjust these three things. So we in this research, I try to use the cyclohexane because in this so far there is no report on cyclohexane based sensors, because it usually it is a little bit toxic material, and also uh, it is mainly used for low dielectric constant. It's a dielectric property is very high. So the researchers are thinking that it cannot render a good electrical response. So in this research, we try to utilize this material, and we succeeded that it gives good electrical response. Electrical response in the sense there is a change in the conductivity or resistance or capacitance. So we took conductivity as a measurement of sensing, right? The sensing means there should be change in any kind of electrical response, conductivity, stability, conductivity, resistivity, or capacitance. So in this one, the cyclohexane mainly consists of carbon and hydrogen chains. So this interact with the analyte. We took two gases as the analyte test gases, the ethanol and ammonia. These two are very important gases found in laboratory as well as in industry, because the ammonia is a very toxic gas. So even small 500 ppm of ammonia is also very dangerous to human beings. So we have to we have to sense these two gases. So that is why we took ammonia and ethanol. First of all, I just explain how we carry out from starting to final. So first of all, it is a polymer-based sensor. So before the sensing material has to be deposited, we have to prepare a substrate, right? So the substrate was the silicon substrate, N-type silicon substrate we took, and then we have to deposit the electrodes. It is like a interdigitated electrode that is given in the bottom, that is here. So it is made up of silver electrode. So that was deposited using thermal evaporation. The thickness of the silver electrode is 21 nanometer, and then we coated cyclohexane on that, and we mask the bottom. We have to mask the bottom line, bottom electrode for connecting with that analyzer. So we just deposited only 2x2 area, 2 centimeter by 2 centimeter area. We deposit cyclohexane in this area, in this region. So what happened? We take silicon substrate, and then we have to make it as we have to mask. We have to use a mask to deposit this silver electrode, and then we load it on the thermal evaporator, and then we coat silver electrode here. So the parameters used for the silver coating is given in the right side. So the cleaning type, first we have to clean using this no need to, we have to clean first the silicon substrate, and then we coat the silver electrode. What happened? And then we use this PECVD, plasma enhanced chemical vapor deposition instrument, because we use the cyclohexane as the source for polymer material. So this monomer, cyclohexane monomer, is transferred to the PECVD apparatus, where it is ionized, and then it is deposited on this electrode substrate, this sensor substrate, and then we get sensor material like this. So this is the actual deposition tool. Inside we keep our that sensor substrate, and then cyclohexane is transferred from by thermal heating, and then it is taken by the hydrogen and hydrogen carrier gases. Once we apply proper RF power supply, and then power 25 watt here, the deposition parameters are given here. So we coat from 5 to 10 minutes, or we can coat from 10 to 20 minutes by using the RF power of 25 watt. Then we can get the different thickness cyclohexane layer. So we check from 5 minutes to 20 minutes, and then after the optimization, we just took only from 7.5 minutes, and then 10 minutes cyclohexane coating was sufficient for good electrical response. And then what happened inside this PCVD? We first send the cyclohexane monomer, and it is polymerized due to the plasma created inside the PCVD. So it breaks the bond. The plasma, due to this electrical energy, the plasma breaks the bond, and then it polymerizes the cyclohexane monomer, and then we get cyclohexane polymer. And then when the deposition power and then deposition temperature or deposition time is increasing, we get this is the sp3ch stretching bond is increasing, which indicates the more and more carbon and hydrogen bond is depositing over there. Okay, what happens? The deposition time when we take uh, the scanning electron microscopic image of the coated surface, the A is representing this 7.5 minutes cyclohexane coated sample, and then B is the 10 minutes cyclohexane coated sample, and then the C is C is showing the uncoated side and coating side. By we have to match the some area. What happens when this coating side? We can clearly show the higher concentration of carbon. It is a small area scanning, so that is why 0.13% concentration of carbon is there. Silicon we can see, and then oxygen is also present. But when we see the uncoated area, there's a small decrease because the scanning area is very small, so there's a small change. That's all. So what happens? We can confirm that the coated side contains more carbon and oxygen elements. And then we analyze the surface area because roughness. It is very important because this roughness, that is very important parameter. Uh, that depends on the roughness. The gas molecules can adsorb or desorb or interact. So this roughness parameter is very important. So what happens? The 7.5 minutes cyclohexane coated sample shows the root mean square roughness of around 0.2 nanometer. And then 10 minutes, the bottom number E, shows the 10 minutes cyclohexane coated sample shows 0.18 to 0.21. That is a small decrease in the roughness. So what happened? 7.5 minutes shows the higher roughness than the 10 minutes coated sample. And also, this is the line scanning profile that is called alpha step. There is an instrument because the thickness is very small. After 10 minutes or 7.5 minutes coating cyclohexane, the coating thickness is very small. We cannot even measure using FESM because FESM uses the electron bombardment, so the coating will easily degrade. So we cannot utilize for thickness measurement using FESM. So we have to go for other techniques such as this alpha stuff. What happens? The bottom one shows the alpha step is kind of electrical scan that it uses a laser to scan from the uncoated area to coated area. So when it is scanning in the coated area source, there is increment in this one. So in this one no coating, and then when the coating coming, it gives the corresponding thickness. So when the stability is coming, we can take it as a measurement of this thickness. So what happens? This is around 40 nanometer. The coating, what I say, the coating area, coating thickness is 40 nanometer, 7.5, and then for 10 minutes it is around 45 nanometer. 5 nanometer difference was there. Okay. We already so far we prepare and then characterized what happened. We try to use cyclohexane in the PCVD on the sensor element, and then we have to go for the actual experiments. So first of all, we have to use the electrical response of the as prepared sensor without introducing any gases. First, what happened? We use just the cyclohexane coated sensor was connected. Okay. Okay. What happened? So this is the semiconductor parameter analyzer. So we have to connect the sensor lead with this one, this parameter analyzer, and then we have to measure like this. We have to measure the I current and voltage properties, IV or VI properties. What happens? Just the as prepared sensor shows the electrical response current in the range microampere range. So at a different temperature from 25 degree to 150 degree, we check how it responds. So the temperature dependent electrical study, we can call it as like this. What happened? It increases. It increases because usually the semiconductor shows the increment in response as due to temperature. So so first of all, we studied from room temperature to high temperature electrical response. What happens? There's a gradual and uniform increase in the current values with respect to the applied temperature. The bare substrate shows the current values in the microampere range. And then more response was noted in the negative region because positive region there was not much electrical response. So we took at only in the negative region it has more response. So the response means the sensing. So we took 1.5 this range 1.5 voltage is better to observe the readings. So the useful operating range would be from minus 1.5 to 1.5. So when we convert this response into a gradual graph, it will come like this. So what happens? Usually we took ethanol and ammonia. So what we thought is 100 degree or 75 degree would be the better range for the actual experiment. So what happened here? That their substrate showed only the microampere range sensing that response, and then we went for the this what happened? The cyclohexane coated. After the cyclohexane coating, we took the electrical response. Here we, here we can see the 10 minutes cyclohexane coating from 25 degree to 150 degree. What happened? The current value was very high. So this means after the cyclohexane coating, the current value increased. We did not, even now, we did not introduce any gases. So, sorry. After the cyclohexane coating, the electrical response was from minus 50 milliampere to 25 milliampere. So when we convert into the data points, it will go like this until 100 degree or 125 degree. If we use 10 minutes cyclohexane coating, it will increase and then start decreasing. So we took in this region from 75 to 100, that would give good response. So this is the actual setup, experiment setup used for this gas sensing. It is we did not use any kind of it is a simple setup. We did not use any mass flow controller to introduce ammonia or ethanol. Instead we use an evaporation chamber. We took ethanol and ammonia as a liquid form. We evaporate here and then we evaporate in this evaporation chamber, and then so these vapors we have to apply some heat, and then these because of this high temperature, we set this one as 100 degree, and then this due to this temperature all gas evaporates, and then it will go to the gas chamber here, and then it interact with the sensor element, and this sensor element will give corresponding electrical response, and that response is measured in the semiconductor parameter analyzer here. And also for every experiment or introduction of every experiment parameter, we evacuate all the gases using a vacuum pump, and then the test gases were supplied newly. So it is, you can see here, this is a small, very simple experiment setup. This is the evaporator chamber, and this is the main gas chamber, and this contains that sensor element. That element was connected to the this IV probe station using copper lead. In the IV probe station, this is the output of this IV using the SPA, semiconductor parameter analyzer. So this is the formula we used to calculate how much liquid is required for making proper or corresponding. If we want to make 100 ppm of ammonia, we should use 38.5 ml. Similarly, for 250 ppm, we have to use it 96.2 microliter. So we vary from 100 to 1000 ppm, and then we check the electrical response. So this is the formula we can use that gives that connect with the density and then volume of liquids, that is the test gases liquid required, and then molecular weight and everything. And once the gases are introduced into the that gas chamber, then we have to measure how in how many in what time the sensor response. So this is the response curve, sensor response curve. What happened? We use different concentration of the gases, ethanol gases, 400 from 1000. From 3 minutes to 5 minutes, we observe that the stability, that sensor response was very high. And then it started, we measured until 15 minutes. What happened from 3 to 5 minutes, the sensors show good response. So after introducing from 3 to 5 minutes, we can start measuring the sensor response. The bottom one shows uh, uh, the electrical, because we should take the we should use a different concentration from 0 to 1000 ppm of ethanol or ammonia, and then the electrical response means changing the current. What is the current value? So you can see that uh, you can see if we use 200 ppm of ethanol, the current value is very high, that is around 65 milliamp, and then for 400 it is increasing. You can see here. So similarly, when you higher, when the ppm is the concentration increasing, the current value is also increasing. So we have to take the change from 0 ppm to higher ppm. That is the change in the current is that is the sensing. Similarly, if we go for this ethanol, so there is a change in the current value when the uh, the concentration is increasing. What happened in the ethanol? Until 600, there is a drastic change in the current value, but after 600, it is decreasing. So this means that the cyclohexane showing good response until 600, but after that it is decreasing. So we can use this sensor for measuring the ethanol concentration until 600 ppm. Similarly, in the 10 minutes cyclohexane coated sample is also showing the similar behavior until 600 and then decreasing. So, but here the change in the current value is very small, 6.35 ampere only. So for measuring, so from these two, what we can say is 75 degree. That sensor should be operated at 75 degree. So this 7.5 minutes cyclohexane coating is better for ethanol sensing. But whereas for ammonia sensing, we can see here ammonia sensing is actually kind of gradual increasing, but the sensing is very small. So the change in the current value is very small. So what happened? What we can say is this sensor is better, is showing good response for ethanol sensing. So ethanol sensing at 75 dB performed using CH 7.5 minutes CH quarter, showing an increase in conduction current until 600 ppm and then started decreasing. It is because at higher concentration, the amount of vapor generated was very high, so that hindered the performance because we are using the liquid form. If you use some other gaseous form, maybe the sensor may show some good operating response. But we use liquid form. That liquid is started absorbing on the surface of the sensor, and then it is disturbing. But an interesting point is to be noted is that the different in the current observed from 0 to 600 ppm was impressively large, which suggests a good sensing. At the same time, the current value was observed very high for ammonia, but there is the difference is only 2.171. That is a small. So it is learned that CH 7.5 operated at 75 degree was good for ethanol sensing. So ultimately what we found was our CS cyclohexane that was quarter for 7.5 minutes in the PECVD. That is very good for ethanol sensing until 600 ppm. And then I just to move on to the next presentation. So can you clear right until now? Hello. Okay. Let's go for the yeah.
Sir?
Can you hear until now? Can you clear until
Yes,
now?
sir, it's audible.
What happened?
It's audible,
Okay.
sir. Just continue, sir.
Yeah, it's audible. Okay. Okay. Next, I would like to move on to the next topic. That is that this is the topic I work for many years. It is about the low temperature plasma, which is used for nanomaterials preparation. Usually, there are many techniques for nanomaterials preparation, such as hydrothermal, sol gel, or some kind of coatings techniques, and then ball milling. But it is a plasma. Plasma means it is an electrical discharge. It is a collection of freely moving charge, but it's a fourth state of matter. So, the plasma is created by applying very high electrical voltage between the high voltage and ground that ionizes the gases which produces plasma. So it is consist of freely moving charged particles. So these charged particles acting on the nanomaterial solution, and then which gives kind of very different size or shape of nanomaterials. So low temperature plasma means we this kind of low temperature plasma is done using the atmospheric condition. We do not use any kind of high voltage or high power. It is just utilize only the very low temperature, means around 25 in the room temperature. So that is called in equilibrium plasmas. So it is electrical discharge. Okay. Usually in the conventional plasma systems, usually utilizing very high vacuum. We have to create lot very high vacuum in the range of 10 power minus 3 to 10 power minus 6 torr, which is even if it is exceeds very high vacuum, that is called ultra high vacuum. That is in the range of 10 power minus 6 to 10 power minus 9 torr condition. We have to utilize these rotary and turbo molecular pumps to create vacuum. But whereas in the case of atmospheric pressure plasma, we do not use any kinds of this vacuum generation equipments. It is just operated in the normal atmosphere. Yeah. So in this atmospheric pressure plasmas, there are many kinds. Those are the dielectric barrier discharge, microplasmas, soft jet plasmas. So what happens in dielectric barrier plasma? There are we have to apply very high voltage in the electrodes from top and in the top and then the ground electrode. Then apply. So we should use only on dielectric barrier because we cannot directly give power between high voltage and the ground. It will create arc that will create arc. So that is not a plasma. So we have to utilize one dielectric. Then what happened due to this power, the gases which are inside these electrodes get ionizes. So this ionization which gives the plasma. So we get a plasma like this. Same thing is a micro. So dielectric barrier discharge plasma is a kind of whole area volume. The volume is very high. The DBD area is very high, but in the microplasma it is kind of filamental. Filamental. Microplasma Microplasma is a kind of filamental phenomena, and similarly, soft jet plasma is also kind of a microplasma. So the soft jet plasma configuration is given here. What happens? We have to apply high voltage in this here and the ground voltage here, and then it should be properly insulated. So we should use a glass tube as a dielectric. And when we use very that high voltage alternating current, we get a plasma. like this. So we call it as a jet because it is coming like tap water. So we call it as a plasma jet. In this condition, we just give only nominal or very. It is not like a very high voltage. It is nominal around 500 voltage we are applying, and the current value is 0.125 ampere. And then the TT percentage means we cannot continuously give the power because it will hit up this electrode, and then this glass tube will get damaged. So it should be operated in a pulse mode. So the we have so the pulse mode, which means on and off. So it is only the 14% the duty ratio in the sense in the total time period how long this plasma is on. So only the 14%. So most of the time it is off. So this means the energy consumption is very low. So this is the electrical VI curve, and then so we have to use some gases to ionize. That will give plasma. So we can use various gases ranging from air or argon or nitrogen, any kind of gases. It depends on the gases we use. The plasma consists of different plasma species. If we use air as a gas, we get nitrogen ions as the nitrogen ion and the electron as the plasma species. If we use argon, that argon is ionized and we get more argon ion and electron as the plasma species. So those species comes out here, and we expose this plasma to our nanomaterial solution. So that interaction of plasma species with nanomaterial solution, that gives rise to different size and shape of nanomaterials. So this is the phenomena we see in this plasma-assisted synthesis. So what happens in this experimental? The experiments are based on the concept of plasma liquid interactions. So due to these interactions, any surface morphology of the nanomaterials could be changed or not. So this is the fundamental idea. So it is our curiosity to use whether the low power soft plasma to alter any physicochemical properties of the nanomaterials. We took zinc oxide and sulfide as a testing material, and also to investigate any morphological changes, because this zinc-based material, zinc oxide and sulfide, is very much utilized in energy, environment, and electronics, catalysis, biomedical. There are so many applications. The zinc oxide and zinc sulfide applications are very wide. So we can use it for many applications. So in this one, size and shape dependent properties are fundamental to nanoscience. So we want to investigate. Initially the solutions, that is the nanomaterial precursors, were prepared separately, and 1 ml of the corresponding solutions were mixed and exposed to plasma. So so this is the plasma system. The plasma will comes out here. We have to mix. Suppose if we want to prepare zinc oxide, so we have to take zinc precursors such as zinc nitrate or chloride or sulfate or acetate, zinc sulfate or acetate, and then one precipitating agent, NaOH or ammonium hydroxide, anything, in a bottle, mix it, and then expose to plasma for some time. Okay, first of all, these are the surface morphology of zinc oxide prepared using zinc nitrate A, zinc chloride, or zinc sulfate without applying any plasma or any temperature or any surfactant. It is just prepared in the normal room temperature. So what happened? Only the spherical surface morphology only was obtained when we for zinc oxide. Suppose if we use very high temperature, there may be a possibility for getting some other structure, or if we use some other technique, we will get some different morphology. But if we do not use any surfactant or any temperature or anything, we will get like this structure. But what happened? Suppose the same experiment was conducted in the presence of plasma, soft jet plasma. So these are the different surface structure we get for zinc oxide. When we also, so this is the, when we take zinc nitrate, you can see we take zinc nitrate as a precursor and then NaOH as the precipitating agent. We use a different concentration from A to C. Here in this range, we use different 0.05 mole, 0.075 mole, or zero point 0.1 mole. So we have to fix nitrate concentration fix and then vary NaOH concentration. And then second one, we fix NaOH concentration and then vary this zinc nitrate precursor concentration. So what happened when we take nitrate, we get different surface structure like this, from cubic, from cube, rod, kind of pillar like, and then like flower like. So what happened? It is that two things are playing here. One is the concentration, and the second one is the plasma impact. So so this is the without plasma, and this is the plasma. So what happened? The plasma is able to provide different surface structure. So that is the main finding here. And also we use here nitrate, zinc nitrate as the starting precursor. Suppose instead of zinc nitrate, we use zinc chloride. What happens? These are the surface structure we get. So here another find is also coming. The raw material, the nature of zinc precursor, that is also very important for getting different nanostructure. So in this one, when you use chloride, we get two kinds of things. One is the rod kind of zinc oxide and a rod, and then kind of flower. Here also we get flower, but here are different structure. And then we go for sulfate. If you use zinc sulfate as a precursor, we get layer-like structure. You can see most of the sulfate precursor gave layer-like structure in the presence of plasma. So what happens? Actually, what happens? How the plasma is interacting with the nanomaterial precursor? This is the mechanism. What we take a nanomaterial precursor, plasma is on for 1 hour. Due to this plasma species and then turbulence, the turbulence in the sense a kind of motion because of this kind of corona wind is forming in the present, even the plasma is on. So the solvent water starts evaporating, which gives supersaturation. Because of this supersaturation, we get when all the solvent evaporates, we get the powder in the form of precipitate at the end of the reaction. The reaction was conducted for 1 hour. After 1 hour, the powder is precipitated at the bottom of the this bottle. What happens when the plasma is on? There is electric field is creating. This is the plasma. The soft jet plasma is called cross field jet. This means around this plasma, there is a formation of electric field, strong electric field creation. Also, the electrons and the electrons that transfers to the solution, which also enhance the electric field. Based on this electric field strength, the precursor ions, zinc ions, orient in a peculiar way, which depends on the concentration and the nature of ions. So because of this orientation, based on this electric field and incoming electrons, we get different structure. Then we get to say like one-dimensional nanorod or flower-like. What happens if the electric field strength and the zinc concentration is lower than any OH concentration? We get nanotube or nanorod. Suppose NaOH concentration is very, very high, we get nanopillar and flower structure. In addition to this electric field, the nature of ions, because we took different precursors such as sulfate, chloride, or nitrate, because of this ionic parameter, ionic means ionic radius and molar mass, ionic radius and molar mass. These two, suppose if you get it is a very high molar ionic radius, it may be the possibility of one-dimensional structure. So there is a complex interplay between this ionic radius, ionic molar mass, and then this plasma species such as electrons and electric field. These are all which gives a cumulative effect, which gives different nanostructures, such as one-dimensional or flower or layer structures. And then we characterize all those nanomaterials using various physicochemical techniques, such as X-ray diffraction, Raman spectra, and then XPS, FESEM. So what happened? This zinc oxide, irrespective of this shapes, this is hexagonal, which gives hexagonal ZNO, and then the prepared nanomaterial exhibit good material structure, because from the from this Raman spectra, this peak 583.4, suppose this is the defect peak, zinc oxide defect peak. This is the main zinc oxide peak in Raman spectra, Raman active mode peak. When we have to compare the peaks between 440 and 583. So if this peak is very high intense than this one, the prepared materials has not much defect. So the intensity of this defect peak is small. So we can say that the prepared nanomaterials is kind of very perfect structure. And then we analyzed this XPS for the chemical functional group or purity of the nanomaterial. The zinc oxide Egerton 2p peak, which this one, that there were three peaks. The first one, 529, exhibit the zinc oxide peak, and the 531 is the oxygen in the that lattice of zinc oxygen. This is the oxygen 1s spectra. So there are three kinds of oxygen were incorporated with the prepared material. The first one is oxygen linked with zinc, that is 529.9 with this one. And the second oxygen is related to the interstitial site, oxygen in the interstitial site, that is the lattice oxygen. And then third is the oxygen absorbed due to the moisture from the atmosphere. It contains small amount of moisture. So ultimately what happens, uh, the prepared material exhibit good crystal structure as from the XRD, and then good structural, and then good chemical purity also. And then let us we use the same concept and same kind of experimental approach for preparing zinc sulfide. So the first one, this one, the if you see the literature, you can see zinc oxide has a different structure ranging from one-dimensional nanoflower and then the layer structure. But zinc sulfide you cannot find like this. You would always find a kind of aggregated structure like this. Even now, there was not much report on different structured zinc sulfide. So we took as a zinc sulfide and then concentration and sodium sulfide concentration. So what happened? Here you can see these are the when we use zinc chloride, we get one-dimensional structure also. So this is the one of the important finding when we use the same soft jet plasma. There are three. 1 minute. Okay, here. Oops. Hmm. Here we used zinc sulfate as the precursor, and then when changing the different concentration, we get, you see, one-dimensional here, like a zinc oxide. We get one-dimensional zinc sulfide in the presence of plasma. So without plasma, there is no possibility of one-dimensional structure. And also we analyze the EDX measurement. The prepared nanomaterials consist of only zinc and sulfide with minor oxygen, and then no other impurities were found. And we check the stability, thermal stability of the prepared structure. We took two model zinc sulfide. One is the spherical kind, or this aggregated structure, and then a one-dimensional structure for checking the thermal stability. What happens? the zinc sulfide, when we increase thermal stability, thermogravimetry analysis, we check the zinc sulfide in initial stages until 200 degree, the evaporation of water occurs, and then around 350 to 400, there is a sharp decline in the the weight of the sample by applying the temperature. That refers to the changes of zinc sulfide into zinc oxide. And then after 400 degree, when we increase the temperature, there is the transition of zinc oxide into metallic zinc was observed. So this is the trend. Zinc sulfide is converted into zinc oxide and then to metallic state. What happened? We have to measure the weight loss because thermal stability is about the weight loss. This aggregate structure zinc sulfide. So suppose if you take 8.1 milligram initially, and then the final weight is around 1 milligram is lost. Here in the 1 structure also, it is lesser than, the loss is lesser than this aggregated structure. So this means the prepared 1 structure is more stable than the spherical structure. And then we check the XRD and XRD spectra of aggregated and then the one-dimensional zinc sulfide. What happens? The spherical structure, the aggregate structure shows the sphalerite, zinc sphalerite. There are two kinds of zinc sulfide was found. One is the spherical structure showed sphalerite, and then this one-dimensional structure was the ursite, hexagonal ursite, zinc sulfide. Okay, so what happened so far in this research, that soft bit plasma was utilized to synthesize zinc oxide and zinc sulfide. The prepared zinc oxide nanometer exhibited different surface morphological features such as nanorod, nanoflower, and nanosheets like. The non-plasma assisted zinc oxide yielded only aggregated spherical features. The starting precursor materials and plasma exposure that gives rise to different morphological structures. So the XRD and Raman spectra confirmed the ursite structure. In terms of this zinc sulfide, there were different structure were also found. The one-dimensional structure, layer structure, and then spherical structure were achieved. But as compared to zinc sulfide, zinc oxide was better to engineer the surface structure. Only zinc sulfide yielded only 2 or 3 kinds of surface morphology. And the zinc sulfide exhibit the band gap of 3.72 and 3.77. So it is only the UV responsive, mainly in the UV responsive. And I want to thank you. I want to acknowledge to the Ministry of National Research Foundation of Korea for giving the funding. And then I want to thank to the principal and HOD and staff members of MEM College for Dindigul. And also we collaborate with many other institutes. Those are Kwangun University, Jeju International University, and our university and NRF for their collaborative helps. Thank you so much for everyone for your patient listening.
Thank you, sir, for your thought-provoking and informative lectures, sir.
Thank you so much.
On behalf of the participants, I am initiating some questions to you, sir.
Yeah.
What is the best pH of ZNO nanoparticle synthesis?
Pardon?
What is the best pH for ZNO nanoparticle synthesis?
Usually, it will be like in the range of 8 to 9. That would be better. 8 in the alkaline range, 8 to 9. Yeah, that would be better.
And then what is the role of NaOH in ZNO nanoparticle synthesis?
It is very important because NaOH is considered the precipitating agent, because if you want to prepare zinc oxide, there should be oxide precursor should be there. Okay, if you want to prepare sulfide, we should have sulfur precursor. So zinc nitrate will be there for zinc precursor, and then for oxygen we should use zinc NaOH. Usually it is a very simple precursor NaOH, or we can use ammonium hydroxide also. Any metal precursor and then one alkaline precursor. So these two will give rise to the oxide precursor, right? So that is the main role NaOH. That is plays a precipitator. Yeah.
Then, some researchers used ZNO nanoparticle synthesis for ammonium hydroxide. Why, sir?
Ammonium hydroxide.
Yes.
I don't understand. Ammonium hydroxide. Ammonium hydroxide is a liquid, right?
Yes.
Okay. But why they use zinc oxide? I don't understand. I think it is very rare. I never have heard like this. Maybe it's very different. Maybe.
Yes. Yes. Then, what is the
Ammonium
role of?
hmm.
Yes, sir.
Ammonium hydroxide is usually like NaOH only. But I don't understand why they are using. Yeah.
Then, what is the role of synthesis of NaOH in ZNO nanoparticles, sir?
Yeah, I already explained.
Yeah, yes, I already explained. Then, one more question, sir. Then, how to identify the circulation performance of materials and the structure of samples after reaction, such as XRD and FTAR for after nanoparticle synthesis?
FTIR, okay. XRD, okay. XRD, it is a very fundamental technique which gives the structural information. Okay. Suppose NaOH, zinc oxide, there that is there are the main form of zinc oxide is a kind of hexagonal structure. We have to use the XRD to identify the structure of the prepared nanomaterials, and also in terms of this is the physical technique, physical and chemical. So usually characterization techniques are physicochemical. Physical techniques are XRD, FESEM, TEM. The chemical techniques are XPS and FTIR. As compared to FTIR, XPS will give more information about the surface functional group, functional chemistry, the surface chemistry. So that is why the XRD is the physical structural technique, whereas the FTIR is for identifying the chemical purity or the surface functional groups of the prepared nanomaterials.
Is there any questions from the audience? Okay, sir. There are no more questions there.
Okay, I thank you very much for everyone for patiently attending my presentation. Thank you so much.
Thank you, sir. Thank you very much. The highest form of thought and happiness is doubled by a wonder called Thanksgiving. As in deliverance of gratitude, I would like to call upon Dr. M. Ramesh, Assistant Professor of Physics, to propose vote of thanks.
Good afternoon. It gives me an immense pleasure to deliver the order for this moment. First of all, I would like to thank our clever principal for wonderful support to us. Thank you, ma'am. Importing knowledge is the prime aim of this program. So, in that way, I would like to thank Professor Dr. M.V.Muthiah Govt, National College, Trichy, delivered an outstanding lecture on magnetic nanomaterials. From this presentation, scholars working in the field of magnetic nanomaterials could gain in depth of knowledge. Thanks a lot, sir. Next, I thank Professor Dr. Anthony Anand, Samkin University, Korea, for his knowledge-provoking presentation on cyclohexane-based gas sensor. The presentation would have turned the scholar to work in that field. Thanks a lot, sir. Finally, I would like to thank our meeting secretary, staff members, and participants for making this webinar as a grand success. Once again, I thank the member of thank you.
Thank you, sir. Once again, I extend my sincere thanks to each and every member of the distinguished audience from your active participation. It was pleasure being with you. Here's some instruction to the participants. The feedback form link is now shared in the chat box. So kindly give your feedback, and feedback is very mandatory for getting an NCE certificate. The certificate will be emailed to you shortly, only after the submission of the feedback form. It's always nice to end things on a bright note. Hopefully, wishing to see you all again on another astonishing sessions. More to go. Thank you. Participants, kindly leave the meeting.
முடிச்சிட்டு வந்துச்சு டெலிவரியா ஒரு தடவை அடிச்சாங்க